Hola, yo soy Horacio Pérez y esto es Investigando la Investigación, un podcast donde investigamos cómo investigan los investigadores, tanto en la academia, industria, independientes. Todo ello mediante entrevistas y debates abiertos, técnicas y estrategias para mejorar todas las partes del proceso investigador y, no menos importante, opiniones abiertas que espero llamen tu curiosidad y te hagan también reflexionar. Hola, muy buenos días. Hoy es ya miércoles 6 de abril de 2022. Hoy tenemos un episodio de entrevista a un investigador que en este caso nos va a hablar de una tecnología que tuvo mucha, novedad en la primera década del siglo XXI, pero que todavía sigue dando resultados que hacen pensar a mucha gente y que encuentran una gran cantidad de aplicaciones en diferentes contextos, tanto científicos como en la industria. La investigación que realiza el entrevistado de hoy tiene que ver con líneas punteras con la investigación en el grafeno. El grafeno es un material que cada vez se le encuentran nuevas propiedades y nuevas aplicaciones. Y para poder hablar de él, tenemos el placer de tener hoy una entrevista con Romain Danneau del Instituto Tecnológico de Karlsruhe en Alemania. Hoy, en esta entrevista, Romain nos va a hablar de la investigación que ha realizado a lo largo de los años mediante el estudio de este material con unas propiedades sorprendentes, pero no solo eso, no solo nos va a hablar de la parte técnica, porque como ya sabéis, en este podcast también nos interesa ver la vida de los investigadores y entonces también nos va a contar un poco su visión sobre cómo se debe realizar la investigación, cómo se debe gestionar un grupo de investigación cuando tienes a cargo doctorandos, postdoc, etcétera, y cuál es su opinión sobre las tendencias actuales en este campo de investigación en el que él trabaja. Bueno, pues os dejo ya con el episodio y espero que lo disfrutéis. Hasta luego.
Good morning, good evening, good night. That's depend where you are listening the podcast from. Today we have the pleasure to have here in our podcast Romain Danneau from Karlsruhe Institute of Technology. Hello, Romain.
Hi.
Thanks a lot for accepting this invitation. It's really a pleasure. Okay, so would you please introduce yourself a little bit?
All right. So my name is Romain Danneau. I'm scientist at Karlsruhe Institute of Technology. I'm physicist by training, and I'm working in Karlsruhe since 2008. And so I'm working mainly on physics of graphene, but also connecting graphene with superconducting materials and looking at their properties at very low temperature. So I'm what one call a quantum transport specialist or low temperature physicist.
Okay, very interesting. And could you make a brief summary for the general audience? What is the relevance or of some practical applications of these technologies?
Well, graphene was actually isolated something like 16 years ago, something like this. And nowadays it has some, let's say, practical application, somewhat in various domain. But let's say it's a very specific material, which is a single layer of carbon atoms disposed in a hexagonal lattice. And they have really funny properties, and it's really a single atomic atom. So it's the first purely two-dimensional material that was really isolated.
Mm-hmm. And yeah, so your research moves around this material, graphene. Is that correct?
So it's about two-dimensional materials that you isolate and pile them on top of each other. So we also work with, so graphene is conducting material, and we usually try to isolate it in between two non-conductive material, namely actually hexagonal boron nitride.
Okay, and what is that useful for?
Well, it has a very, I'm really trying to look at the electronic transport, how the electrons propagate into the material, and it can be a very clean system. So you can really look at transport of electrons in a ballistic way. So when they do not encounter any inelastic scattering, and so yeah, it's quite specific. So you don't see that into that many materials, let's say.
Okay, and this property, so that electrons or this kind of particles can, let's say, run freely into the material, which advantages provide to materials in real life, in practical life, that we can see every day?
Well, let's say me, I'm more into trying to make them superconducting, so they really do not undergo any dissipation. So you know that basically when a power plant produces electricity, when it finally ends up to your house to turn on your light or things like this, what was produced from this power plant, 30% is lost. So imagine that if you have a superconducting materials that carry the electricity, there would be just no loss.
Oh, no loss. That will be really great. And are there any plans? Are there any plans at the moment in order to change this current power infrastructure in order to change it for materials like graphene? Is that possible?
No, because graphene is actually not a superconducting material. So I try. So you might be able to connect graphene with a material that is superconducting. Of course, unfortunately, superconductivity only appears at low temperature, or more or less low temperature. So you can induce superconductivity in a material over a certain distance. So what you can do with graphene is actually to tune its conductivity with a third electrode called gate, and which is exactly the same principle as a transistor, basic component of microprocessors, for example. And so you can indeed, if you can induce superconductivity in this material, you can also tune the superconductivity in the material with this extra electrode.
Okay, so it could be translated so that a relevant material can be kind of mixed with graphene in order to improve its properties.
I wouldn't say that it improves the property. It changes its property. You make graphene it is by definition a very tunable system. And in the case of my research, it's really turning it to a superconducting system that is highly tunable. You can make it superconducting and not superconducting.
Okay, very, very interesting. So, in which domain could you say that it's being used really a lot at the moment in practical real life applications?
So in practical applications, I cannot tell you that there is any real practical applications, but in terms of for scientists, you can design very like single photon detectors. So imagine that you have a detector that can really detect a single photon. That is possible with this material. It's very sensitive up to the point that you can detect only one photon.
Oh,
That's one of the application of this sort of devices.
Oh, that looks impressive. And now going to your research, now that we understand the relevance of these materials, can you summarize how do you do your research about graphene? What do you do? Do you try to use in addition to other materials, or do you study some specific properties of graphene?
So a bit both. As a scientist, you try to actually, let's say, prepare a certain experiment. Sometimes you get what you wanted, but actually very often you don't get what you want, and you have to understand what you are doing. And so that's also a large part of the work we do, is to try to understand what really actually happens. Me, I'm doing very fundamental physics, so it's a bit far from application. But yeah, so I'm really trying to use graphene as a medium for superconductivity, as a tunable medium, because you can design different small circuits that are highly tunable thanks to graphene. But on the other hand, sometimes we obtain, let's say, not necessarily expected results, which are really due to the specific properties of graphene. Then we tackle really fundamental properties of the material itself. So it really depends. So either we use just the faculty of graphene of being extremely tunable, from something that conducts very well to something that does not conduct at all, to really tackling very specific inner properties of graphene. So it really depends. It's kind of like twofold.
Twofold, right. And as you said, sometimes you plan an experiment, you have some hypotheses, and then you do the experiment, and either things don't work, or you obtain unexpected results, etc. This is what happens to me on my research most of the times. Could you mention some example in which you obtain totally unexpected results, and then it turned into something relevant or interesting?
Yeah. Well, okay. So, for example, not so long time ago, I asked my student to prepare a given device with specific, let's say, specs, and in the end, it turns out that the device had a very, let's say, special characteristics that we did not expect. And instead of focusing on what we planned, we actually switched completely to almost another dimension, and we exploited this for actually really long. So we did probe the device in many ways, but really only based on these very specific characteristics that we did not plan at all. So it's a bit difficult to really explain that in a very general term, but it's really you have to be pragmatic and really try to tackle something that is interesting, that is really not expected, and sometimes it happens, and so it may keep you busy, because indeed, since it wasn't planned, you really have to do much more effort to understand really what you're doing, what you finally see if you see something completely new. And it's not like you base your research on from our side. It's more like we have a theoretical paper that predict this or this, and we try to figure out whether these predictions were right or not. And we try to do it, but in the end we obtain possibly what was expected, possibly something different, possibly something that we actually cannot reach, because theorists, they make calculations that sometimes are far from reality. Unfortunately,
I know.
yeah. So it's so you try to exploit a result that you did not expect, and that's usually when things are, let's say, the most difficult for a scientist. I would say, at least to me, because you have to make, for example, or you have to ask a theorist to make the model for you, to explain or to find an explanation about what you have observed, and so it's not necessarily it's actually not easy.
No, it's not easy at all. It's not easy at all. But as you said, from a point of view, it can be very interesting. Okay, you make some prediction. I'm also, let's say, theoretician. I make some prediction about what I think is going to happen. That somebody measures something in the lab, and then what is measured is totally different from my prediction. How can I feel? I don't feel bad. I mean, this is just what happens. This is reality. This is science. Then from my point of view, one should analyze and try to understand why my prediction didn't work, so that I improve my model or anything. And I mean, it can be very, very interesting. The main problem I see is the following, that I don't know if it happens to you. When you apply to grants and you have a project, you plan the project. I'm talking about some of my examples. 2 years ago, I applied to the funding agency, and then the project is going on, but you have we have to follow exactly that plan. So we cannot deviate from the plan, even if we find something interesting, which is something that I don't really like. Because sometimes this unexpected result, if you can spend some of the resources of the project into that direction, can lead to way more interesting results at the end. So that's my impression. But I would like to have that scientists could have more resources in order to sometimes let's say explore these unexpected situations. I don't know what is your opinion.
Yeah, well, let's say when you work within a project and you have certain targets to reach, of course, politicians that provide you the money to do your research also know that, well, you expect to see something, but you actually may not reach the point you wanted. But usually in grant application, you also should provide some sort of intermediate goals, and these intermediate goals can bring you some also results that you can exploit, which are not the final target, but that is something that is, let's say, satisfying enough, and that you can, let's say, in the end, the funding agency are, let's say, of course, they want you to do your plans, but they also are aware that you may try to do something extremely challenging in a given limited time, and sometimes you have been a bit too optimistic somewhat, or like, I don't know, COVID appear and things are delayed, or I don't know.
Exactly.
You don't know what may happen in your life, and but they want to make sure that you can have these sort of intermediate results that you can exploit, that are also very interesting, even though they are not really the final target that you try to reach.
Right. Yeah, right. I totally agree, and I think this what you said is a very important advice. If you apply to some grant, just to put some lines about that you could follow in principle some unexpected deviation if it could lead to some interesting result, of course. But trying to accomplish first this milestone, these things that you propose at the beginning.
Yeah, exactly.
Yeah, very important. And and you said before, I'm not going to tell you about this because this is going to be very technical. Anyway, can you tell us a little bit this what happened with you and your student in technical details? Probably there is something in the audience that will be interested on this. Just as if we were physicists in your field.
In my field. So
right.
Let's say I consider myself being really what I call a low temperature physicist. So I worked at low temperature though then, and actually at millikelvin temperature, so very close to the absolute zero. And for that you need specific equipment. So namely a cryostat, actually even namely a dilution refrigerator. And so we play with a system that can bring what you try to probe close to the absolute zero. And of course, you don't probe something at this extremely low temperature as you do that at room temperature. Because as you try to probe your device, you inject a bit of current, and of course, current actually dissipates. And of course, if you have heat in your device, well, you will heat up the entire system, and well, you won't be at low temperature. So you really have specific techniques. You have to use extremely low noise electronics. You have to use extremely tiny signals to avoid the heat of your device. And so everything has to be under control. It's quite technical, and it really, you have to develop some electronics sometimes, your own electronics, your amplifiers. You may want to bring them at low temperature to reduce the noise of it, the noise that can be directly reflected to your measurements. So it's quite some technical work that you have to handle. So it's not purely necessarily plug and play thing. You really have to
I guess, but it looks really, it looks really complicated. Because it's very difficult to reach the zero Kelvin. It's impossible according to third principle of thermodynamics. It's impossible, but you have all these problems because I don't know. You set up this system, and some car is in the street moving, just going on, and it can affect your measurements. It can be really complicated. Is this, by the way, the same system or infrastructure in which quantum computers work?
Exactly. So most of the system that, at least the solid state quantum computing or the solid state qubits, they are cooled down to millikelvin temperature, so to really few tenths of degrees, close to the absolute zero. So yes, let's say you really need to avoid having a thermal excitation in your system. So you have to go to very low temperature. On top of that, so far the best qubits, the best series of qubits, they are made of superconductors. And so that you really have to be at very low temperature for the material you are using.
So does it mean that the research that you do could be potentially applied to quantum computing systems?
One could say that, yes, somewhat. But it's really it's a bit like looking at new transistors for a microprocessor. So microprocessor has billions of transistors in it. So I'm at the level of a single transistor with respect to the microprocessor. So it's really very specific.
Okay. Somewhat. And in your research, one of the problems, as I can understand, is the setup of this infrastructure, of this cryogenic system. But is that the main limitation? apart from the money for research, of course, that because this is some problem that we all have. But is that the main problem, or are there others that limit your research?
Well, of course, the technique. Let's say, technically speaking, you always have limitations. For example, for me, temperature is not a limit, but it could be if I would like to go to a lower temperature for whatever reason. I can go to a certain temperature, but not below. So that would be there are some certain things that I just cannot do. That limits what I want to do. But also on the device fabrication, because it's in my field, it's really you design your device, your small electronic circuits, and then you probe it, and these two things are not easy. So, and both are very technical. So you first have to use. In our case, it's what we call micro or nano fabrication, like the basically techniques that are commonly used by the microelectronic industries. And so we design very, very tiny circuits, and then we have to connect these circuits, and we have to connect these circuits to our cryostat. We cool the cryostat down, and we can measure it at this low temperature, and then you need a very specific electronics, very specific techniques to probe these sort of transistors.
Okay, it looks complicated.
Let's say it's a long process. Let's say, of course, it's. I would not say that complicated. To some extent, but of course it's a lot of things to do. You have to be very careful. We all carry charges in our body, and one thing you should avoid is to discharge yourself into your device, because it will suddenly have a large amount of current flowing through it, and you may just blow it up.
Okay. Wow.
So you have to be careful. You have to let's say ground yourself, okay, and don't touch a large piece of metal.
Right.
I don't know if you open your computer, if you touch your motherboard, you also have to be careful, because it's actually full of electronic devices that you can blow up just by actually touching it, and because you have charges, and the potential difference between you and the device might be deadly to your computer.
Okay, so we will take care the next time that we work with our supercomputer. Okay, and this question would be, what do you think are the next breakthroughs or the main research directions that will go in the next decade in our field? I mean, I guess one of them is related with quantum computing, but you are not on quantum computing. You are in the study of these systems. What do you think what is going to come in the next years?
Well, let's say, somewhat. Quantum computing is of course one field that receives a lot of funding at the moment.
Right.
Whether there will be a quantum computer working anytime soon, that I have no real clue. But what can come next, I'm not fully sure. It's sometimes it changes very quickly.
Yeah.
It depends on the new discovery that may occur. The new technologies. Sometimes progress comes from the technology that is being developed. So it's I would say that's quite of an open question. So I'm working in something that is what is called nowadays quantum technology. But I've been working on that before it became somewhat trendy. And I guess I will most likely continue to work in this field after the fashion changes to something else. So I'm not fully sure. At the moment, for example, a lot of people are working on batteries and developing new batteries because of course we know for electrical cars and things like this. So things should change a lot. So lots of money also goes to batteries. So it's completely different to what I do. And I guess it's also something that will be renewable energies and things like this. Making better solar cells. Finding like new technologies. It's something that also can be very useful somewhat, and I guess that will continue like this for a while.
Okay. And I have another question. I'm a chemist, a computational chemist, but there is some chemistry here and there. Graphene is a material composed by carbon atoms in some specific, let's say, configuration. Okay, but I read just by chance that there are some other materials kind of similar to graphene, but which are not composed by carbon atoms, but for silicium, beryllium, and some other atoms. What do you think about this? Is kind of the same properties, or do you think this is a promising research line?
So you mean, for example, replacing carbon by silicon?
Yeah.
And that people call that silicon.
Right, exactly.
So I'm not really sure if people have managed to really actually produce a single layer of silicon. So the thing is, graphene always existed because graphene is actually a single layer of what is called graphite. And graphite is in your pencil. Graphite has been used in a nuclear power plant. You can mine graphite, but no one before people in Manchester managed to really isolate a single layer of these atoms and connect it and pass current through it. So they were the first people to do that. As far as I know, I don't think in the nature, for example, silicon has its two-dimensional form available. I don't think you can find it in the nature. So for graphene, it was somewhat natural.
Okay.
But I was talking about a bit earlier. I was talking about this hexagonal boron nitride. Okay. And hexagonal boron nitride, it's actually almost exactly like graphene, but instead of having carbon atoms, you have a boron atom and a nitride atom. You have these atoms disposed in the two sublattices, and but they have absolutely different electrical property. One is a conductor, not the other.
Okay, I think I read about this silicon. I don't know if this is borosen or this kind of stuff.
Yes.
In kind of computational papers. There is some researcher from the north of Spain called Ángel Rubio, I would say, and he performs a lot of simulations and calculations in order to predict these properties. I mean, I know this. Yeah. I know this by chance. No,
no. Maybe people try to grow it. I'm not sure whether they actually grow it in a. I mean, they can really form some small islands, let's say really tiny islands made of these, for example, silicon atoms disposed in 2 dimensions, or they really manage to make a large film. A large film, I actually really doubt. I don't remember seeing that. I guess I would have noticed it. but no, on two-dimensional materials, it's this transition metal decalcogenide that are somewhat quite popular at the moment still. It's not exactly a single layer of atoms because it's not perfectly two-dimensional somewhat. It's not really a single layer of atoms, but they have also some interesting properties. At least by the fact that they are by structure semiconductors, most of them.
Okay. And another question, I'm very curious about this. Sometimes you said that the only that graphene is the only one that has been found in nature, but sometimes
compared to this silicon and there are other 2D materials you can find in nature. No.
Right, but for instance, in this astrochemistry, people look at the stars, and then by spectroscopic studies, they study the light that comes from the stars, and sometimes they detect some molecules. And I don't know if you know by chance if they have detected in the interstellar space graphene, at least as a fragments or something. If these structures, I don't know.
I actually think it has been observed, yes. Carbon nanotubes, I'm pretty sure, and I think graphene as well. Yeah.
Wow.
I actually know an astrophysicist working exactly in this kind of topics.
Does it mean there is alien life?
Well, who knows?
Who knows? Wow, it's an interesting discovery. Okay, so now, can you tell us, Romain, when? Let's talk a little bit about you as a researcher. When did you decide in your career that you wanted to go into research? Was it while doing your PhD, or before, or later, or when it happened?
As far as I remember, it came out, let's say, very progressively. I never planned really anything. I just took the opportunities when they somewhat came to me, or when I sort of provoked them. I guess it was at least partly when I was, like, let's say, in middle of my PhD, when I got lucky that things were working pretty well for me at very early stage. And so I quickly decided to try to stay in the academics, knowing that I had to do a postdoc, so obtain my PhD, basically going somewhere else. So personally, I went abroad, and I wanted to persuade myself that I was able to do research on my own, somewhat.
Okay,
and I managed to persuade myself, and of course, unfortunately, in the academic world, it's not because you want to work in the academics that you actually work in the academics. So it's not because you want that you can. It's all about opportunities.
Yeah, exactly. That's very important. But sometimes people, for instance, some mostly PhD students, they get a little bit, in my experience, depressed because they see how long and difficult is the trajectory before you can get a permanent position as a scientist. So yeah, this is complicated.
That is definitely a very long way, in particular in the country where I'm working on. It's I don't know. I became officially permanent scientist fairly late, for sure. And so you have to accept this kind of let's say Yeah, it's difficult when you have a family, when you you even don't work in your own country. It's definitely not that easy. So at least I can tell you that in Germany, very, very few students, at least as far as I can see in my institute, go for a postdoc position after they obtain their PhD. Very few, very few.
You mean they go mostly for industry?
They go to industry, yes. In let's say in Germany, since there are quite a lot of jobs, at least since I'm in Germany. So for a student who obtains its PhD, it doesn't seem to be that hard to find a job in industry. But in other countries, it's not that easy, and so people end up to have a postdoctoral position by default because they don't find a position in industry. I think that's not super good, but that's the way it is.
It's not super good, and that's the way it is. Okay, and before you said that you got the permanent position somehow late, but what does late exactly mean? If we can ask.
For me, I was 43.
43. Wow. Yeah, but this is kind of unfortunately something normal, right?
In Germany, it's fairly common, I would say.
It's fairly common, right?
Yeah. In France, it would be quite very late. I don't know anybody in France who got telling that because I'm French, but I don't know anyone who got a permanent position at this age. Me, it was really some sort of like official age. I got to know that I was becoming permanent earlier than that, but as long as you don't sign your contract,
exactly.
You're not fully sure.
Exactly. And you said before that you went abroad for your research. In which countries did you do your research?
So I moved to Australia first. Wow. And so I spent three years in Sydney. So coming from Grenoble, so I did my PhD in Grenoble in France. And I'm originally from Paris, so I studied in Paris. And so a long way to go. So it was very adventurous, somewhat. But also some sort of like a dream was coming true for me because since I was a kid, I always dreamed about going to Australia, and used to have the map of Australia on the wall of my bedroom, and I always said to myself, I will go there once.
Okay, that's good to have these objectives. Wow.
And so I got the opportunity to go there, and I say, okay, let's go. Let's say, nowadays, if you want to stay in the academics, I would definitely not do things the way I did. I was a bit, naive somewhat, but it turned out to be right, and it turned out to be good for me. I had a very great experience, I think, and I traveled quite a bit.
But why do you say not to try to be naive?
Well, because when I said to people I went to Australia for a postdoc, people think that I studied surfing or something like this. So it's more like a place for holidays than to do low temperature physics. So it was at least very much like this when I came back from there. Well, it's like a lack of credibility. So let's say you better go to a fairly renowned place if you want to sell yourself afterwards. I don't know, in a fancy American university or a very renowned place. That will help you. On the other hand, my thought was more about I wanted to go to a not that known place to perform my own research somewhat. So actually, when I was in Australia, I got my own grant, so I could really perform my own research somewhat. Although it's always relative, but yeah.
Yeah, but I mean, sometimes people is obsessed with research for the postdoc in the United States universities, but sometimes I don't know how to say this. I have the feeling, this is personal opinion. Sometimes I think it's better to be in a place where you can feel happy or feel good. Like in your case, you wanted to go to Australia, so but at the same time you could do science there. Okay. That's also, I think, from my point of view, is important for for people in order to have very good life experiences. Because some people go to the United States, spend some years in a very competitive university in the United States, but the ambient is very toxic. They don't enjoy the place, and at the end, sometimes there are stories I have here, and they end up leaving academia or something. So I think
it's, let's say, this competitive environment and so on. It's I would say it's very general in the academic world, not only in the US. Wherever I've been, after being in Australia, I moved to Finland. I worked in Helsinki for 2 years. Country is very, very different. But overall, it's still academic world, and it's still quite competitive. It's still, you're still scientists. You have to be productive. You have pressures all the time, in particular when you're not permanent. But even now, being permanent, if you want to work properly, you need still to be productive. You need to raise money. So it's. But it's a trend. You need to also enjoy your life to be able to work properly. It's fully true.
Yeah. Okay, so you went to Finland, which is, I guess, a good country for the study of low temperature system. It's a very bad joke.
You can
know.
Really say that. But I was in a low temperature lab. It was called so.
Okay, and then you moved finally to Karlsruhe.
Yeah, so it was really. I never dreamed to work or live in Germany, but it just happened. So
it happens.
It's I don't know. It's I met someone who advised me about the position I got, and I finally applied. I went there. My interviews went pretty well, and so I got the position, and finally turned to permanent staff.
Okay, so now you are in Karlsruhe. You have a permanent position. You do your research. You are leading a group there. And then, how do you spend your time mostly in management, in the application to grants? How much time do you finally have for research at this stage of your career?
I would dare to say that research is also about management, about grant application. And I think it's also a part of your let's say, of the research that you do, because managing the students, for example, or postdocs, interacting with them, you also have to teach them how to do research. You have to show them things. You have to advise them. You have to guide them. That's mostly how I see myself. For the grant application, well, you don't write grant applications without having certain knowledge. And this knowledge, you actually use it for your own research and for your future projects. So I think it's a whole thing by itself. So, but of course, research, it's about, in my case, it's about experimental work. It's about understanding the physics of what I'm doing. It's about writing articles about treating data, about performing really the experiment. In my case, cooling down my cryostat and things like this. So it's every day is rather different. That's also one reason why I enjoy what I do.
Mm-hmm.
It's not like every day is the same. It's I can manage my time in a very different way. So I do really various things.
Okay, and how do you? I'm curious. How do you manage your time? Because as you said before, in the life of research, there are many things to do, very different things to do, totally different. How do you manage this? Do you have a plan in advance about the things you will do during the week, or how do you plan this?
Well, let's say I must admit that I'm possibly not the best guy for time management. It went up to the point I actually, when I think I was in the UK, I bought this book I have in my hand, which is called Managing Time. Oh. And I tried to save my time because I thought I was like dispersing myself too quickly. Sometimes I deal with something in the end. I think it's not the right direction, so I should change. So I try to be more efficient. So I read this book. I sort of figured out how to apply this to what I was doing. But in the end, I wonder whether it was just myself who I was worried about what I was doing, the way I was doing things. I was thinking that I was wasting time, but actually maybe not that much. So now I think I'm much more, I don't know.
Experienced
somewhat, for sure. And let's say, yeah, I can bear wasting time. No, like things that do not work, well, they do not work. And when it doesn't work, well, you actually learn something. You learn not to do it again. Okay, exactly. So it's you learn out of your mistakes, and mistakes I do plenty, I guess, like everyone.
Like everyone, yeah, totally. Right. And what is the part of your day that you enjoy the most regarding your research?
I'm French. It must be lunch. But
lunch. That's very important.
For sure. No, I'm kidding. I don't know. It's I like having a good. I like having a good scientific discussion with someone, and finally realizing that I possibly understood something. Like So that is, or not necessarily discussing with someone. I could even like read a paper and then read an article for the first time you read a paper, you say, that sounds interesting, but I don't think I understood everything. So I read it again. I still think it's interesting, but not sure if I understood everything. I read it the third time, a fourth time, and then the fifth time, suddenly I kind of realized something. And maybe not I understood really everything, but I think I understood something. And that gives me a lot of satisfaction somewhat. So when I realized that I kind of got a new knowledge, a new way of understanding what I'm doing.
I think that's very important when one is on research and one decided to go on research for this long career to enjoy this kind of parts of the work. Otherwise, it's very hard to keep so many years.
It's like in everyday life. You have to try to stay positive, to be optimistic. Otherwise, I doubt you can go forward.
Yeah, totally agree. Okay.
Sometimes it's not that easy, There's plenty of parts that I do not necessarily enjoy, but I don't know. I try to I try to turn things in more enjoyable way. I don't know. It's you have to stay positive and.
Any tip for staying positive, mostly for PhD students that are listening now to the podcast?
To me, the extremely important thing, and I would say it's of course for PhD students, but for everyone, one thing that is very important in doing research and science, it's staying motivated.
Right.
It's the most important thing. You might not be the smartest person in the world, but you will still try to understand things. You will really make progress. You will. To me, it's really motivation is the big thing.
Right.
It's if you're not motivated, then you should not do research.
Right. Yeah. I totally agree. I would only perhaps warn when people are too optimistic and then they are facing a dead end road and they don't realize about it. And they are constantly crashing their head against a wall. So sometimes over-optimism from a point of view is not beneficial. But some optimism, as Romain says, is kind of mandatory if you want to keep on this. Yeah.
You still have to be realistic. So there are things that are possible and others that are not.
Okay.
I guess.
Yeah, I totally agree. So, I think it's getting very long. We are past the usual 30 minutes of the show. So now, Romain, we usually have, we ask you now if you want to leave a question for the next researcher that we will interview.
And I don't know who's going to be the next one, yeah?
No, you don't know, neither I do.
All right. So and possibly an interesting question, right? I'm not sure.
Yeah. Well, why not?
Why not? Maybe since I personally I think I had some time management issues. Mm-hmm. I would ask the next interviewee whether she or he has a trick to manage its own time.
Okay.
Within a day, which is not only your time in the lab or at your institute, but also with your family. Me as a scientist, I very often think about my work wherever I am. It can be with my family. It can be when I'm traveling wherever, in a train, in a metro, in a bus, in a plane, in my bed.
Okay.
In front of my coffee in the morning. So, and I sometimes even wake up at night thinking about experiments or things like this. So I don't know how other people are dealing with these kind of issues.
Okay. Very, very interesting question. And then, so I take note of this question. And I can briefly tell you that one of the next people that we will interview here is an expert on productivity. So this question comes perfect for the next show. Okay, thank you, Romain.
You're welcome.
Okay, so in the episode, in the notes of the episode, you will find all information about Romain, his lab, his publications. We will add some links to most of the things that Romain said about graphene and his lab. And well, thanks for listening. Thanks, Romain, for accepting the invitation to the show. And wish you a lot of success and enjoyment in your research. Thanks a lot.
Bye-bye.
Bye-bye.
Gracias por estar ahí y por escuchar este podcast. Os recuerdo que en la nota del episodio tenéis los detalles sobre muchas de las cosas que hemos hablado hoy y también un formulario donde si quieres puedes opinar sobre el podcast, para bien o para mal, como quieras, estás en todo tu derecho, y también sugerir si quieres un próximo entrevistado o tema que está relacionado con la investigación, claro, pues tu opinión me parece muy importante, tanto a mí como a toda la audiencia de este podcast que va creciendo y que va contando muchas cosas interesantes. También comentar que si te interesa alguna de las técnicas que hemos mencionado hoy de manera muy breve en el podcast, me puedes contactar directamente y te puedo dar más detalles. Y por último, si te ha gustado, te agradecería muchísimo que lo recomendases a quien veas que le puede interesar y difundirlo por las redes sociales o donde sea. Y nada, y si estás en Apple Podcast, pues ponernos ahí 5 estrellas o 4 como quieras, siempre viene bien. Muchas gracias, hasta luego.